So I would like to introduce our third speaker, Professor Shang. Ray received his bachelor and a PhD from the University of Science and Technology of China. He worked as a joint training PhD at the University of Tokyo from 2012 to 2014. And then he served as a GSPS fellowship in the same department, working with Professor H. Nakamura. In 2017, he was promoted to be a lecturer at the University of Tokyo, and in 2022, as an associate professor. So research interest covers new catalytic reaction, novel conjugated molecules, and their material functions. He was selected as an early career advisory board member for the Science of Synthesis in 2022, and a GSP fellow of the Birkenstock Conference in 2022. Ray recently received the Young Chemist Award of the Chemical Society of Japan and the Chemistry Award BCA 2022 from MSD Japan and the Teammate Chemistry Journals Award 2023. And today, I think Ray will speak with the title, Iron-Catalyzed New Transformations and their applications for electronic materials. Ray, we didn't see your slides yet. Ray. Yeah, but now it's the presenter show, and also I cannot hear you. Yeah, I think that this happened. Oh, now it's perfect. The slide is perfect, but you still need to hear
me now, right?
Okay, yeah, the sound is coming. Okay, now everything's everything's.
So everything's fine, right? I will start my presentation now. Eh?
Yes, please.
So, thank you very much, Professor Yu, yeah, for your very kind introduction. So my sound is clear, right?
Yes, it's clear.
Okay,
please go ahead.
So this is Shang from the University of Tokyo. So today I think I would like to introduce you our new results on iron-catalyzed transformations and its application for making conjugated molecules useful for us to develop organic electronic materials. So it's freeze there. So at the beginning of this talk, I would like to give you an overview of my talk today. So actually, all research focused on iron catalysis. We work on discovering new reactivity, and we synthesize novel pi conjugated molecules, and also we try our best to develop the new functional materials by discovering the function of the molecules. So in this talk, I will introduce my work into two parts today. So part A is the iron-catalyzed CH-CH coupling for the conjugated polymer synthesis through the CH activation. So we discovered some new polymers as high-performance whole transporting materials for perovskite solar cells. So the part B is, I will briefly introduce part B, the iron-catalyzed tandem cyclization reaction to construct this highly stringed, I'll use the laser point, to construct this highly stringed 1,4-dihydropentane skeleton. So by using this method, we created a high homo bisiphon unit so that we can develop very narrow band gap materials for near IR, so near infrared photodetector as near IR absorbing materials. So first, I would like to introduce to you our conductive polymer synthesis by using CH-CH coupling reaction. The reaction is catalyzed by cheap iron and mediated by aluminum as a base. So talking about this conductive polymer synthesis with structure precision and monomer generality. So the current reliable and controllable method is the metal-catalyzed polymerization using cross-coupling methodology. But the method needs a pre-functionalization of the monomers. Yeah, we use dihalide bismuth organometallic reagents, which is very costly and a lot of side reactions here. So it's difficult to control. And the catalysts of high cost, such as palladium, as polymer products, we need any capping procedure to remove the terminal metal or halide. But the polymer, and the reactions generate also this salt and metal salt as a waste there. So our approach is below. So we want to use iron. We use CH substrates, and we use the CH activation method on these linker moieties. The linker moiety can be a siphon or can be arcing, so we can make functional conductive polymers. This is our strategy. So actually, why we started this research, or starting point to make this conductive polymer using iron-catalyzed CH is actually to make polymers starts from our methodology study on iron-catalyzed CH-CH coupling. So in 2019, we reported the first twofold like CH activation cross-coupling using just a 1-to-1 ratio of the CH substrates. But the reaction achieved exclusive selectivity for cross-coupling. There's no homo-coupling observed. So we used a very mild like 1,2-dichloroalkene as a terminal oxidant to turn over the iron catalyst, and the reaction is reduced specific on C2 position. We didn't observe any C3 position of the CH bond on siphon get activated. So interestingly, so different from the reactions using other late transition metals here. So we work only on iron. So the iron-catalyzed system is very good to apply conjugated, especially electron-rich conjugated siphons as substrates. So this makes me feel very interesting. This gives me a hint actually, probably, for the polymerization. It means like the more conjugated oligomers will work better, will not decrease, at least not decrease its reactivity towards the catalyst. So we can make monomer to oligomer and oligomer even to polymers. So of course the problem is that if we have this bidentate directing group, it's not something desirable in polymer synthesis. This is directing group. So inspired by our very old results, actually the 2016 when we published the work, we inspired by this our discovery on carbonyl directed CH activations. So we discovered that diacyl oxalate is a very good oxidant for siphon CH-CH coupling. So the reaction uses iron-3 salt as a catalyst. The tridentate phosphine ligand originally developed by us as a ligand, and we use aluminum, trimethyl aluminum as a base for deproton CH activation. This is also discovered originally in our lab. And critically, this diacyl oxalate is unique oxidant. So with this reactivity discovered, and also my experience working on this electronic conjugated materials, I was thinking that where should we go here? So then I realized actually beyond the sustainability and the cost issues we always emphasize for iron catalysis, actually from chemical point of view, there are inherent advantages of iron catalysis for conjugated material synthesis. This iron-3 actually has very weak interaction with the pi system. So the diprotonative CH cleavage is suitable for large pi conjugated molecules, it means, yeah? And the selectivity is always determined by the acidity of the CH bonds. So if we consider large pi conjugate systems, one of such choice is, of course, is polymer synthesis, is conjugated polymer. So the second is this iron turnover needs a very weak oxidant, such as this dichloroalkene and this 1,2-dicarbonyl compounds. So this is also this comes from the inherent low redox potential of iron-1, iron-3. And this is a critical point to work on pi extended molecules, which has high homo levels. It means the molecules, especially donor molecules, easier to get oxidized. So our first target is how we can apply the iron-catalyzed CH-CH homo coupling for the CH-CH polycondensation reaction. So in order to do the polycondensation, we need to understand the CH activation and dimerization reaction very well. So here I show the working mechanism. So the abundant metal, iron and aluminum, both are very cheap here, and cooperated together. So we can see from the scheme that the first is a twofold CH activation on the siphon C2 position with the iron tridentate phosphine complex. We use trimethyl aluminum as a base to deproton the CH bond. Then the reductive nation gives the bisiphene, which is very easy. But the key is that the catalyst turnover by an aluminum oxalate complex, so which results in the generation of a very stable, like the aluminum indiolate species. So this step actually turns over iron species back to valence 3. But actually, this oxidant is not essentially oxidative, I may call it, towards other substrates, even the donor substrates. So on this page, I will show you some of the representative examples here. So the reaction has very high reduced selectivity. It only takes place on the C2 position of the siphon, and remarkably, it tolerates aryl-tin bond. Of course, it tolerates aryl-bpene and aryl-silane, and this reaction is totally orthogonal to the show reactivity. And by using this reaction, we can make like this electron donative whole transporting material for perovskite solar cell. So many of the tridentate phosphine ligands acquired actually fail in polymerization. So by using this benzofuryl substitute tridentate phosphine ligand, finally the polycondensation works smoothly. So the iron residue we can reduce it to very low contents, like just less than 40 ppm of the iron residue detected in the final polymer. the generality and for the polymerization is a very important issue. We know that is a problem for the radical and the shell type polymerizations, to which limited the monomer scope. So on this slide, I show you the several representative scopes examples for the iron-catalyzed CH activation reaction. We can say it tolerates several functional groups, and we can use it to make like regio specifically alkylated polysiphons. And we can also make a copolymers by applying different monomers together. We just put the monomer into the reaction, so we get the copolymers, but it's a random copolymer. It's not a sequentially controlled polymer. So regarding to the polymerization mechanism, so the iron-catalyzed catalyzed polycondensation proceeds through a step growth mechanism. Because of the very weak interaction of the iron-3 with the pi system. This is our hypothesis, actually. So this is in contrast with the chain growth mechanism, such as we use palladium. The palladium always sticks to the end of the polymer, so the polymerization goes through a chain growth mechanism. So one donor polymer we made by this iron-catalyzed CH polycondensation is a new polymer. So we found it's a very good material. It's an excellent material as a whole transporting material for perovskite solar cell. So we achieved a 21.3 power conversion efficiency, and especially this VOC is very high because of the very good energy level matching of this polymer with this perovskite material. So I talked about the homocoupling for homopolymerization here. But if we get like selective CH-CH cross-coupling, in principle, we can make sequentially controlled copolymers by cleave two different CH bonds for copolymer synthesis. So here I will introduce our recent study on the siphon enamine copolymers, which is a new type of polymers. So here I show the mechanism of this enamine siphon CH-CH coupling. The reaction system is similar to the siphon CH-CH coupling, but the difference is that after the first CH activation, the enamine here works as a nucleophile to attack iron-3, and this generated iminium species alpha CH bond get easily deprotonated by this methyl anion to generate this intermediate, the alkylated iron intermediate, and then it undergo reductive elimination to give the product, and the turnover of the iron is similar to our previous case. We use oxalate and aluminum combination. But this reaction is very different from the mechanistically from the palladium catalyzed Fujiwara Monitani reaction, such as that's another like CH alkylation process. So I briefly introduced the scope. We can see the reaction. We can access a broad scope of this unprecedented cyanide enamine linkage in trans configuration. But how to make this? We can just put visible light in. On the light, there is a photochemical equilibrium, so we can get also both cis and trans product. And this reaction, by using this reaction, we can get some very electron-rich materials, which is easy to get oxidized, but it survives under all reaction conditions. So besides vinyl carbazole, we can also work on vinyl indoors and vinyl like purol, and we can even work on vinyl like diarylamine. So the reaction has very good generality considered enamine substrates. So by using this enamine siphon heterocoupling here on this slide, I show only one example of copolymerization. So we can make this vinylene type of vinylene incorporated enamine siphon copolymers. This is a polymer of entirely new backbone because it's not so easy to make this kind of enamine siphon linked structures, and it's very difficult to make polymers. So currently we are thinking about searching some collaborators to further explore the device or some other functions of these new polymeric materials. So on the next slide, on the next part, I will introduce the other type of iron-catalyzed reactions for the synthesis of conjugate ladder molecules. That is the tandem annulation reaction to construct this highly stringed 1,4-dihydropentylene skeleton. So one of our motivation actually is from the materials development. We developed the methodologies for material synthesis is to develop the reaction to make these 4 fire membrane fused siphon molecules. We call it dihydropentylene disiphon. We will abbreviate it as CTV. So it has a very high HOMO level, and so that is it's a very good electron donor. But because it is a high HOMO, it can be easily oxidized by any chemical oxidant. So there's no synthetic method we can access this molecule. But the solution is here. The solution is from the another advantages of iron catalysis. That is to construct the conjugated ladder polymer iron catalysis. We can utilize this reductive elimination from this ferrocycle to form this very good reductive elimination ability of iron-3 to form this string-like string ring. Actually, this has been utilized by Chiric and co-workers to construct the cyclobutene. So we use this reductive elimination ability of the iron-3 ferrocycle species. So this page we show the mechanism of the tandem cyclization. So we have this sequential tritium methyl OMe bond activated, and we access this intermediate, this F intermediate. On this intermediate, we add the DCP oxidant, which we use for CH activation. So this is the oxidative-induced reductination, and finally we construct this highly stringed ring system by using iron catalysis in 92% yield. It's a very clean reaction. So that by using this tandem cyclization, so followed by the established synthetic sequences like stannylation, styrocoping, and Novinger condensation, so we made this new type of very narrow band gap of non-fluorine acceptor, which absorbs above 1,000 nanometer in wavelengths. So this non-fluorine acceptor, so materials with modification, we may call it engineering of the side chain. So finally, it functions as very well as the organic near function as very well as a acceptor material in the organic near infrared photodetector. So the device fabricated in Mitsubishi Chemical Company actually achieved even better performance in terms of EQE and the responsivity. We use this commercially available silicon, like inorganic silicon EIR photodetector as a reference standard. All material works even better. So we also extended this annulation method to one-port Tetris annulation reaction, so that we can make this siphon, disiphon, this conjugated molecule. I think it's very difficult to synthesize if you consider without this message using this method. So this molecule, how we call it CPDTV, it has the highest HOMO level among all the non-disiphons. This is the disiphon with the highest HOMO level. So here I show the summary of my research. I worked on iron catalysis in Japan, and also I studied organic electronic materials. Finally, from the property of this iron, the reactivity of iron, we used advantages of iron, and with the understanding of the electronic properties of this pi conjugate materials. So we come into this new direction we are currently exploring. So I would like to express my special thanks to Professor H. Nakamura, giving me lots of support and lots of guidance. So thank you very much, Professor Yu. So thank you very much. I think I control time perfectly.
Thanks, Ray. Indeed, you have a perfect time control. And thank you for such a really inspiring lecture with a powerful iron catalysis and can apply in the materials. Thank you so much for the lecture.